Hello, Narnach here. Welcome back to TIS-100 for everyone. The last episode I covered signal pattern detector by live coding a solution. I followed that up with a more optimized version that I thought of overnight. So this episode we're going to continue with the sequence peak detector. So let's have a look. What is a sequence peak detector? This will have an input stream of numbers which are zero terminated, and we have to write out the minimum and the maximum values for each sequence. The minimum goes out here, the maximum goes out here, and the numbers will come in here. And as you see, the sequence length is arbitrary. It's never zero, that's something I noticed. The lowest I've seen is a sequence length of 1. But it can be as long as anything, doesn't really matter. So we have to set up a way that deals with this problem for arbitrary lengths of solutions. So we can't really take any shortcuts in that regard. So this problem is something that I haven't really been able to decompose it into very clean, scalable solutions just yet. And checking the solutions on Reddit, someone managed to scale this by using 10 nodes. So that's probably all 9 of these and maybe this one or that one. So that to me it implies that they found a way to make this solution more scalable. But this solution is pretty good enough to get started, and it will show you how it works. So what are we doing here? Well, I started by working backwards. So I need to send out numbers. And I need to store the numbers, and then anytime a new number comes in, it replaces the one that's been stored because it's lower or higher, depending on if you want to store the lowest or the highest. And if it's a 0, then you need to actually retrieve the value that has been stored as lowest or highest and send it out. So that's a bunch of logic that I've tried to put in the bottom nodes. For most of the solution, actually, this node and this node together, they form one unit and they are the same. So these two and these two are more or less the same. The only difference here being this one checks for the smallest number, this one checks for the largest number, but for the rest the logic is identical. And up here all we do is just make sure that we send the number down this pipe and then copy it to the side and send it down this pipe. So this is a standard store and accumulate and then send it out twice pattern. So what do we do? I've managed to use a lot of labels here, that's for sure. And also, I think in a previous video someone mentioned in the comments that you could inline instructions after labels, which if you see how many instructions there are here, that's actually a requirement, at least for the solution I came up with. You need every line to have an instruction. So inline labels are very useful. So I forgot who you were, but I thank you for pointing that out, because it's probably one of the key points to actually solving this one. You need a lot of instructions. Okay, so let's get started. If we're looking for the minimum value in a arbitrary length chain of numbers, that will have at least one item. That's for now that seems a sane assumption. So the very first number is always going to be the lowest. Why? Because if you initialize it to 0, all the numbers will always be above 0. So you need to set the initial value. You cannot just go and replace it as you find numbers. The first value is a special condition. And that's why I've labeled this one init, which stands for initial. And this is the very first thing that happens. So we take a value from up, and for now don't worry about this one, just focus on the logic in this bottom node here. So we take a number from up and we store it in the accumulator, after which we save it, which means we copy the value to buck. Buck is going to be the location where we store the value that we eventually want to send out. So that's going to be safe, and in ACK we do all our manipulations. So first number that comes in, we store it into BAC because that's at that point the lowest number we have encountered due to the fact that it is the first one. Okay, so then let's move on. Main loop. This is the one that will be churning and churning and churning until we terminate our string of input values with a 0. Okay, so we take another value from up, we store it in the accumulator, and then if it's equal to 0, this number, then we flush it. Because as I said, the sequences are 0 terminated, so we keep repeating until we have a 0. So this is a termination condition. And that's it. We have flushed all the way down here, and all we do here is we do a swap. So BAC and ACK are swapped. So then the value that was stored, we flip it around. We have our, it is then in ACK, and then all we can do is remove the value from ACK and we send it down. So the value that's been stored, we send it out. And then we loop back around and we fall into init, which is exactly what we want. Because afterwards, we basically start with a clean slate. We grab a number from up, we put it in ACK, and then we save it. So we overwrite whatever was in BAC. Because remember, if we flush, then we swap these two. So the 0 value here, we swap it into BAC. And whatever we had stored in BAC, it moves to ACK. And then we send it out. So after the flush, BAC is always 0, which is exactly the same as the initial condition. And because we loop back around and go to init, we store a value in ACK and then we save it to BAC. We always ensure that after our init, BAC is in a sane state and it's not a 0. Okay, let's move on with the rest of the logic. So in case the next number is not a 0, so the first value was a 14, the next one is a 73. So we have a 73 that we just moved into ACK. And we come to the conclusion, well, okay, 73 is not equal to 0, so let's move on. So in this case, we swap. So 73 goes to BAC, and whatever we had stored in BAC, which was 14, swaps into ACK. Okay, at that point, we do a save. So the original value of 14, we overwrite BAC with it, because we don't want any weird values to be in BAC. So this basically, the input we got, we reset it, we ignore it. We just restore whatever we had stored as the lowest value and make sure that, because the next one we do is a compare. And I've labeled this for convenience. I don't actually reference it anywhere. But using labels like this inline, it does help with figuring out where the logic is. Because the thing is, what we do here, we subtract another number that we can get from up. And for now, just assume that the number is going to be the same, because basically all this does is replicate the number, the desired number of times. So we take the number again, so 73, we get it from up. And that's what we subtract from the value that we stored. So in this case, 14 is the number that was stored, 73 is the number we are seeing if it's lower, so we deduct it. Well, 73 is way larger than 14, so the resulting number is going to be highly, highly negative, which is an indicator that the number is larger, so we don't care about it, so we don't want it. If it was in reverse, so let's say the number that we had stored was 73, and we are trying to see if 14 is smaller. Well, if you have 73 and you deduct 14, you end up with 59. Yes, 59. So that's a positive number, and that's always the case. The only time, if you take the stored value, you subtract whatever comes in next. If that is a positive number, so if it's greater than 0, then that means that value is smaller than what we had. So in that case, we jump over to the section I've labeled store, where we take the value yet again from up. I did say there's a lot of repetition with getting numbers in here. And we push it into ACK. after which we save it to put it into buck, and then we jump back to main to grab the next number and see if it's larger. Okay, so if the number is not greater than 0, as in the situation here, 73, or 14 minus 73 becomes a negative number, so that's not really a good thing. So then the next input we actually just discard it, because we always need to process the number the same number of times. So if it was greater than 0, we take the number one more time from up and we store it in the accumulator to save it. If we're not jumping to store, we still need to accept the number that this node is going to give us. So that's why we take it and we send it to nil. Nil basically means we just throw it away. And after this, we also jump to main. And that covers all the logics in here. So let's recap. The very first number, we need to send it through. We get it once. After that, we go to the main loop. So if we look at the node above, I've labeled this one as well with init and with main to see, help remind what actually happens here. So the initial number, we take it from up and we send it down. We just pass it straight through. We don't put it in accumulator. We don't broadcast it multiple times. It just goes straight through. So that's this one. We take it from up, put it in ACK, and we save it. And then we go to the main loop, which is going to be the next number. So in here, in the main loop, we take the number up, we put it in accumulator, and we send it down once. So that's the same thing here. So the move up here corresponds with this very first move, ACK down. Okay, then we do a jump if equal to 0, and then we have to flush it. This gives different behavior. So if it's equal to 0, then we have found this 0. That means we don't need to do any checking, we don't need to do any comparing. All we do is take the number that was stored in buck and we send it out. For the rest, we don't care. So we only need the number once, because afterwards we loop back and we go back to init. So that's exactly what I do here. If the number that we just that we have conveniently stored in ACK, if it's equal to 0, we just jump to init, because that mirrors exactly what we're doing here. Okay, if it's not equal to 0, we move on. So in this case we do a swap and a save, and then we move, and then here we have a subtract up. So once again, same number in ACK, we send it down for this subtract from up. Okay, in that case we have the jump if greater than 0, which will go here, which does a move from up. And if we don't do the jump, we have another move from up to mirror that. And that's where the second one in this chain is for. The move up nil might seem redundant, but the thing is, up here you don't have a way to discern what the difference is going to be in the stored numbers. You can't, in this point, you can't know if the jump if greater than 0 is going to trigger or not. So for that purpose, it's easier to just send both of them, rather than basically mix the logic of this one and this one, so that we can save one instruction, because it's just going to be more instructions. So in this case, we always send it down twice, and after that we jump back to the main. Because we don't go to the init, we go to the main, because we're still in the middle of a sequence, and the next number needs to be emitted multiple times. Unless it's a 0, in which case it terminates early. After which we go to the init and we send one number through for free. So yeah, this is less straightforward than earlier solutions, I think. It's a relatively tricky solution, and it's only I started by just working the problem from the end, building a storage engine that could just store a number that would flush on a 0, basically to just build it in pieces. So first you store the number, and my first chain of outputs would be just 58, and then a 56, and then a 60, just basically the last bits in the chain. And gradually I added more and more of the conditions and more of the just the multiple outputs until the entire thing was done. So if we run this, you see 308 cycles, 6 nodes, 48 instructions, which places it a bit cycle-wise, it's almost efficient. Node count is also pretty common, though people have done it better. So that next I started optimizing. So let's have a look at this one. This is a 5-node solution. So before there was a bunch of logic over here that was repeated over here to feed the 2 core nodes that were actually doing all the work. So I decided to condense it because there was enough space in this node to actually do most of the logic twice. So this number now just sends the number down rather than splitting it. And this one just passes the numbers it gets from the left and sends it down. And all the logic for splitting is now in here, while the logic down below is still exactly the same. So the initial value is we take a value that we get from up, we store it in the accumulator, and then we send it down once and we send it to the right once, after which it gets passed through. So init is slightly more complicated because we actually still need to use the accumulator for this. And then we go to the main, where we do exactly the same. And after that, if the number is not equal to 0, because equal to 0 means we flush it and we're done, then we send the number down and to the right twice in succession. After which we go back to the main and the whole thing repeats. And this is, as you might imagine, it's less efficient on the cycle count, but we use less nodes. And instructions, I think it actually went down by a little bit. Yeah, it saved me 4 instructions because I use a whole node less, so there's less repetition of instructions. Well, as you've come to know by now, I like to optimize for cycles rather than nodes and instructions. So I have one that's optimized slightly for that as well. This is not perfect. I mean, as I mentioned before, I've seen on Reddit, I've seen people post scores where they reached 220 cycles using 10 nodes and 46 instructions. Personally, I haven't seen the solution. I only saw the score in the list. So assume from that what you will. But I did manage to do some optimization, and that's the main optimization here is basically that I've inlined the main loop. So we still have just taking the instruction from up and we send it down, and then we have the main loop here. And then basically what it was before, I didn't have the non-zero label here, and rather than this inline thing, it was a jump main. So it was basically just ignore this. This is exactly how it worked. I can actually just run it. It should still work. It's not sufficient, but it still works. So if you can compare this and this, there are 2 steps in the main loop. The first thing is processing the value, sending it down once, because you always need it once down below. And then we do a check if the value is 0. So afterwards, you can basically say, well, okay, we've entered a new section, which is for the non-zero value. Because if it's a 0 value, we go somewhere else. In this case, we jump back to the init. So this is the non-zero value processing area, which we send the number down twice, after which we jump back to the main. But the thing is, jumping is inefficient, because it's an instruction that doesn't contribute to sending values through, doesn't do any calculations. All it does is move where the execution pointer is in the code. So if you have a lot of space left, and in this case there are 5, 6 lines left, and the labels are spaced pretty inefficiently, so to say. So there's 7 spaces here. So you can inline the main loop, so that's these 3 instructions. You can inline them, so the jump main, you replace them with these 3. And then you need to change how the jump condition here works. I'll get to that in a bit. So if you do that, you basically get this solution. So non-zero, move ACK, and then we get the inlined main. Again, I've just labeled it for convenience. And that also helps to show, okay, this is an inlined version of this. So the actual instructions, the moving from up ACK and ACK down, are the same, up arc and arc down, but in this case the jump is different. Where here you jump if it's equal to 0 to init, so you jump over here. And otherwise, so if it's not equal to 0, you go to non-zero. So because this one is now located in a different spot, if you reach this place in the code, then if it's equal to 0, you want to go to the init. But because it's at the end here, if you fall through, you already go to init. So basically, if you don't do anything, it always jumps to init. But if it's not equal to 0, this code here would fall through to non-zero, because that's the next bit on the line. So that's why, in this case, you use the J and Z, the jump if not 0 instruction, to jump to non-zero. And then you have a pretty darn efficient bit of code, because there are no jumps in here that only redirect the control flow without making key decisions. So a jump if equal to 0 is a decision maker, because depending on the value, you do one thing or the other. A jump main doesn't make a decision, it always does the same thing. So if you can inline sections of code, then it becomes a better solution as a process. At least it becomes more efficient, because every jump you make, it costs you cycles, because it's a dead cycle that could have been used for something else. And especially if it's let's say a critical section that other bits of the code are waiting for output from here, then the more efficient you can make your loops, the better it will be, because the other sections of the code will be waiting less for them, and subsequent sections of code will be waiting less for them, and so forth. So all those little changes, they have an impact. So in this case we have 287 cycles using 6 nodes and 52 instructions. So 287 is the fastest solution I've gotten to so far. I know 220 is now a nice goal, and I know I can try to get there by using more nodes. That's at least a hint the way I read it. And if you look at it, what could you do to make it more optimal? Just thinking out loud now. I haven't actually tried it, but I'm thinking out loud. Basically as an exercise for the reader at home or the watcher at home. If you wanted to optimize it further, what could you do? Well, currently, if you look at idle percentages, the node here is running 33% of the time it's idle. So distributing it causes a bit of a delay. Here it's 21% idle, so this is doing something most of the time. And in the bottom we're only idle 15% of the time, so it's hardly ever that we're not doing anything. And if I actually just undo this bit, so we jump main. This is the old logic, this is the new logic. Let's see if we can see a difference in the idle percentages. So let's go back. So this one is idle 18% of the time, this is idle 21% of the time. So it's always more busy. It's probably because it's a blocking factor, because of course this one is distributing things equally. And if this one takes more time to do the same thing, then of course everything else is just going to wait for this one to get done. So that's a way to look at the code to see what you can optimize. In this case, no, this is the lowest idle percentage, so it bears some optimization. So if we run it again, this is no longer the slowest node. Actually, this one is, followed by this one. So the bottom two nodes are the slowest. And there's a lot of inefficiency going on if you just look at it. I mean, the ACK and BAK were just swapping in and out quite a lot, moving new values, things like that. There are things going on that, no, they basically are there to work around the limitations of the simplicity of these nodes. and I think in previous videos, previous puzzles, most of the time you can work an ACK-BACK setup out by just using an extra node and using that for storage. And you just send stuff in, send stuff out, and if you know what the flow / rhythm of things is going to be, then you might have a more efficient way to deal with it. So as I had before, I had a node that you could send a number in. If it was a 0, it would send out the number that was already stored. And if it was not a 0, it would just store the value it got. So basically you have a storage node. That's something that you could build just to the side of here. And then this one, rather than just sending out a number 1 or 3 times, it would be basically just pipe the number through either 1 or 2 times. Or maybe even just pipe it past the side to directly put it into storage. So this one can just focus on only comparing. Because that's probably the key thing. This one does multiple things. It compares, it stores, and it sends the number out. But comparing 2 numbers is something that could be completely dedicated into a separate node. Storing numbers is something that can be stored in, it could be done in a completely separate node. And the control logic to decide between comparisons, result of comparisons, what to store, what to flash out, that could be a third node. If this logic in here then would be split among multiple nodes, that would also mean that this node would have a lot less to do. Because currently all it does is just pipe numbers through 1 or multiple times. But if a bit of the decision logic would be passed from here up to here, basically if you have a storage node here, for example, or a comparison node, then you can push things around a bit. So I think for optimizing it further, that is a interesting direction to research. Again, haven't done it yet, but that's an exercise for the reader. So yeah, as you notice, earlier videos I usually tried to work out the best solution, the Reddit perfect, as I've come to call them, solutions before posting videos. But if you've noticed, it's been 3 months since the previous video. So it increases the time to make one of these videos by a ridiculous amount, because these puzzles are getting more complex and it just takes too much time. In this case, I'd rather put out a video with a good enough solution that shows you the basic concepts and then give you a hint of what you could do to possibly optimize it. And then just use the comments below this video as a place for discussion, where you could discuss possible ideas or solutions you found with other people and just celebrate different solutions that way. And with that, I am going to thank you very much for watching. If you haven't done so already, hit the subscribe button to stay up to date for videos that I post. I post multiple videos per day, usually 1 or 2. Now currently it's the winter break for 2015, so I'm posting 4 videos a day. Different genres, different things, and I just have multiple series going on at every time. TIS-100, as I said, it's been on hiatus for 3 months due to getting stuck on just trying to optimize puzzles and just taking way too much time, and some issues with my recording software. I've got most of that sorted out now, so for now I'm just going to focus on getting working solutions, doing a couple of optimizations, and then just sharing what I've discovered with the community, rather than not sharing anything because I can't get it perfect. So that's it for now. I thank you very much, and I hope to see you again in the next video of TIS-100 or of something else. Bye bye.